Hello and welcome to Spring 2016 weather training for air traffic controllers. And once again this spring we're going to be covering thunderstorms, and our topics will include a review of thunderstorm characteristics and hazards. We'll talk a little bit about the cause CCFP changes in 2016, address a few weather radar concerns, and review some new online products for monitoring and forecasting thunderstorm development. So how well do you know thunderstorms? This presentation contains an informal 10-question quiz. If you'd like, and it's not required, you can stop this module now for a moment and grab a pencil and paper. Just keep track of your answers and give yourself a point for each right answer you get during the module. At the end of the presentation, we'll add up your points and rate your storm expertise. So let's get started with question 1. About how many thunderstorms are occurring at any given moment around the world? 300, 900, 1800, or 3600? And the answer is C, 1800. That's roughly equivalent to 16 million thunderstorms per year over the Earth. Obviously, thunderstorms are an extremely common weather phenomenon, but familiarity with them may make aviators forget just how much caution is needed when routing through an area of thunderstorms. There are 3 basic ingredients we need to produce a thunderstorm. These include water vapor, unstable air, and some source of lift. And so how do meteorologists determine how much of each ingredient we have? Well, for water vapor, we look at forecast profiles of humidity and the temperature dew point spread in different layers of the atmosphere. For unstable air, what you want to look at is the vertical temperature and humidity profile and determine whether there are layers that, when pushed, would continue to rise on their own. It's important to note that moisture adds to this instability. The more moisture you have in the atmosphere, the more energy you have to lift into a thunderstorm. And the lifting process has to get started somehow. And this can usually get started with the presence of fronts or troughs in the area, or maybe the presence of some fairly decent daytime heating, such as in the afternoon with the sun. And also jet streams can dynamically help the lifting process. There are 3 stages of development and dissipation for thunderstorms. There's the towering cumulus stage, the mature stage, and the dissipating stage. In the towering cumulus stage, the cloud develops. It's mostly updrafts, and the expansion of the cloud is often visible with the naked eye. In the mature stage, now you've got the presence of ice crystals at the top. The cloud is developed so high that it's moved into a very cold region, and you get the appearance of the anvil. You also see the rain shaft appearing at the bottom, and the updrafts and the downdrafts within the thunderstorm cloud are at their peak intensity. In the dissipating stage, the thunderstorm takes on a fuzzy appearance. It consists primarily of downdrafts, and the rain intensity starts to weaken. It's important to note that thunderstorms can pass through all 3 of these stages in as little as 30 minutes. So thunderstorms do represent rapidly changing atmospheric condition. It's important to track how these thunderstorms are developing and dissipating, therefore, when you have thunderstorms in the area. Question 2. Routing over the top of a thunderstorm in a towering cumulus stage of development will safely avoid turbulence. Is that true or false? And the answer is false. In an average developing thunderstorm, the updrafts can travel as fast as 6,000 feet per minute. So therefore, the area above a developing storm cloud may contain severe turbulence. The cumulus stage is where the visual observation can be as important as radar in avoiding turbulence. Developing cells often have sharp, distinct cloud edges and can be seen building and expanding. As a controller, it's important to be aware of areas where thunderstorms are expected to build. These areas can be quite turbulent immediately prior to strong echo development on radar. So let's look at the different types of thunderstorms. The first type we'll look at are the single cell thunderstorms. These consist of a single main updraft that is quickly replaced by a downdraft once precipitation begins. They're usually short-lived, maybe around 30 minutes, and the majority are sun-driven. They're sometimes referred to as pulse, popcorn, or air mass thunderstorms in the absence of strong fronts. And here in the Minneapolis region, they're the most frequent in the late summer, and then also in the late afternoon and early evening. What makes them difficult for aviation purposes is that their precise locations of development, like near an airport, are often hard to predict. And obviously their timing and location can be critical to traffic. If we look at this particular situation, where you have thunderstorms developing near Chicago, the air mass development can get complicated when you have outflows from single cells that interact with outflows from other cells. And it's unorganized development like this that is often not well forecast hours in advance by models. So it presents a real challenge for meteorologists in trying to get ahead of isolated thunderstorm conditions. The second type of thunderstorm is the multi-cell thunderstorm. These usually occur along a front or outflow boundary and can last for hours. The individual cells mature and are carried downstream by upper winds. New cells will form upwind from the previous cells and take their place. And it's important to stress in these situations that cell movement may be different than area or line movement. The cell moves forward, but the area of lift may be shifting more slowly. So when someone like a pilot asks, how fast are those thunderstorms moving, the answer can often be given in two different ways, either in terms of the cell movement or the area and line movement. An extreme example of this is where you've got training echoes. This is where the lifting process is shifting so slowly or might even be stationary that training echoes may occur. Each of the thunderstorms will follow the path of the preceding storm. The cells move, but the area does not, and this can create large rainfall amounts over a short period in a small area, which may lead to flash floods. Obviously, if this occurs over an approach to an airport, it can be very tough on air traffic management. Squall lines occur where you've got the area of lift shifting rapidly. Thunderstorms will form in a line which can extend laterally for hundreds of miles, and the squall lines will persist and move for many hours because you've got a constant source of lift, the front, and then they can produce damaging winds and hail. Gust fronts and damaging straight-line winds are common, and this type of thunderstorm is most common in the Minneapolis region in the late spring and early summer. The third type are the supercell thunderstorms, and these are the main source of severe weather. The updraft speeds in a supercell can exceed 9,000 feet per minute, or close to 100 miles per hour. And these can be found also in conjunction with multi-cell clusters and lines. The instability in lift is so strong inside a supercell that it can form its own rotating mesoscale circulation, sort of like a miniature low-pressure system. The rotation of the storm may actually be visible, and you can have extreme wind shears and extensive turbulence with these storms. They also generally will have tops above 45,000 feet. Another type of thunderstorm we should talk about doesn't necessarily fit into these other categories are the nocturnal thunderstorm development that we get in the Minneapolis region. These correspond to the strengthening of what we call the low-level jet over the Great Plains, and they occur after sundown. That kind of counterintuitively, because normally you think of thunderstorms developing during the heat of the day. After sundown, the winds increase rapidly from 1,000 to 5,000 feet above something we call the nighttime inversion. And when you have low pressure over the Rockies and high pressure to the east, this will increase the moist flow coming from the Gulf of Mexico over the plains. This can result in increasing instability and the development of nocturnal thunderstorms. Sometimes they will develop into an MCS or mesoscale convective system. This is a large broken area of multiple cells covering hundreds of miles. The jet stream that helps produce these thunderstorms will weaken after sunrise, slowing the moisture transport. So frequently what happens is after the sun comes up, these storms start to dissipate and the whole system weakens. These systems can produce severe weather and large wind shears, which result in turbulent areas on the north and east sides of the thunderstorms. And again, normally these systems weaken rapidly after sunrise, but they often foreshadow additional thunderstorm development in the same region later in the day. So question 3, microbursts and gust fronts are only associated with supercell thunderstorm activity or the kinds of thunderstorms that cause severe weather. Is that true or false? And the answer to that is false. Microbursts can be found under small or any thunderstorm. And one example of a fairly small thunderstorm that can produce a severe microburst condition are the dry microbursts that occur in the western United States. These thunderstorms will appear weak on radar, but flying under these thunderstorms can cause loss of control of an aircraft and result in a fatal accident. So these hazards can be found with any thunderstorm: hail, low-level wind shear in the form of microbursts or gust fronts, lightning, icing, or turbulence. Hail is associated with a sustained updraft in the front part of a thunderstorm, most frequently with multicell or supercell type storms. Hail can often be found aloft but not at the surface. It can be encountered in clear air several miles from thunderstorm clouds, such as under blow-off or anvil tops. It can fall as fast as 100 miles per hour. And the states with the highest hail risk include western and southern sections of the Minneapolis region. Another hazard is the low-level wind shear. Wind shears or abrupt changes in wind direction or speed can occur at any altitude, but they are most dangerous when they occur next to the surface. It's technically defined as a change of wind speed of 10 knots or more per 100 feet in a layer more than 200 feet thick, which occurs within 2,000 feet of the surface. A severe low-level wind shear is an airspeed loss or gain of at least 15 knots and or altitude loss of 500 feet per minute. That leads us to question 4. At the surface, a microburst is an area of A. Diverging winds, converging winds, upward air motion, or D. No winds or motion. And the answer is A, diverging winds. A microburst is an area of diverging winds at or near the surface. It starts out as a downdraft, which quickly accelerates and strikes the ground, and the downdraft moves away from the point of impact. These cover an area less than 2.5 miles along a side, with a peak wind as high as 170 miles per hour or 150 knots that lasts 2 to 5 minutes. It's important to stress that the strong wind shears associated with a microburst are often non-recoverable and can result in serious aircraft accidents. A gust front is related to a microburst because it's the leading edge of cool air rushing down and out from a thunderstorm. We saw examples of this type of gust front or outflow boundary when we looked at those isolated thunderstorms near Chicago. The abrupt wind shift actually can occur miles away from the parent cell and look something like this. You might have a shelf cloud associated with a gust front. Generally, and here's question 5, generally an aircraft flying into a gust front will tend to A. undershoot the runway, B. overshoot the runway, C. abruptly decrease altitude, or D. flip on its side. And the answer is B. It'll tend to overshoot the runway. A gust front is an area of converging winds that are near the surface. The wind shears in a gust front are usually less critical than a microburst, but they can be zones of severe turbulence. Typically, your headwind is often on the approach to the runway, and a plane that's encountering that sudden increase in winds will tend to experience lift and cause the airplane to overshoot. The next hazard we want to talk about is lightning, and it's important to note that most lightning strikes do not cause damage. The current is generally directed along the outside skin of the aircraft. Any damage you get from lightning usually is limited to outside punctures, electronics, maybe damage to the navigational equipment. But one of the important points to stress about lightning is that airlines have to inspect aircraft after a lightning strike. This can cause flight delays with or without damage, which can run into money for the airlines. Another thing to remember is aircraft can induce lightning strikes. The lack of observed lightning with high-topped echoes may not mean no lightning for a flight approaching a cell. So question 6. Most severe icing inside a thunderstorm cloud occurs in the anvil blow-off, in the rain shaft, between 0 and minus 15 degrees, or between minus 15 and minus 25 degrees. Which is it? The answer is C, between 0 and minus 15. These are where you find the supercooled liquid water droplets. SLD, or supercooled little liquid water droplets, freeze on impact with an aircraft. The clear icing accumulation can be very rapid when you've got large droplets like these. At high levels in a thunderstorm, the icing from smaller droplets may be rime or mixed rime and clear, but it's important to point out that it's those SLDs that produce the severe icing conditions, and virtually any thunderstorm will contain these conditions somewhere in the cloud. Question 7. To avoid thunderstorm turbulence, the best route for a plane to take around a cell would be over the top of a cell, on the upwind side, on the downwind side, or under the cell. And the answer is B, on the upwind side. That's because downwind areas around a thunderstorm contain the most extensive turbulence. And recognizing that it's not always possible to route safely on the upwind side, if routing downwind, a rule of thumb some pilots use to avoid the cell is to avoid it by 1 nautical mile per each knot of wind at flight level. A 60-knot wind, therefore, would mean a minimum distance of 60 nautical miles downwind. On the upwinds and other sides, the area within 5 miles of a cell is worth avoiding, and that sometimes is a greater distance depending upon the altitude and PIREPs. A minimum 20 nautical miles is often recommended when flying above 20,000 feet and in an area when you're penetrating an area between cells. So question 8. The Collaborative Convective Forecast Product, or CCFP, is a collaborative forecast by AWC, CWSUs, and airline meteorologists. Is that true or false? And the answer is false. Since 2015, the CCFP has been a completely automated product. It is the consensus of a number of computer weather models. Your CWSU meteorologist no longer has input into this product. We do have input into the Collaborative Aviation Weather Statement, or CAWS. And so what's changed with the CAWS? Beginning March 1st, 2016, the CCFP is the focus for generating initial CAWS statements. Every 2 hours, the CCFP is reviewed for accuracy. CAWS advisories will be issued where the CCFP is not accurate and national traffic impact is likely. So what we're looking at here in determining whether or not the CCFP is accurate, we're looking at confidence, coverage, timing, and tops, and the fact that those differences will have national impact. Also be within the strategic time domain, 2 to 8 hours into the future. And another criteria is with the tops. Tops have to be forecast at or above 25,000 feet within 100 nautical miles of a core airport, or the average tops at or above 34 for all other continental U.S. stations, and represent a 50% or greater level of confidence. So let's take an example here. We have a CCFP that just shows thunderstorms over the southeastern part of the U.S., and we're expecting thunderstorms actually to also occur along the east coast. We will then issue, if we see this on the CCFP missing the thunderstorms, we'll actually issue the cause graphic that includes a set of times and tops for the area of thunderstorms, and include a summary and discussion about that area with that graphic. Question 9. Anomalous propagation or false echoes is filtered out of the warp radar display. Is that true or false? And the answer is false. Known ground color patterns are filtered out. However, AP is still a problem for NEXRAD, the National Weather Service radar, which warp uses. However, AP is generally easy to recognize because of its random, non-contoured patterns and lack of movement. Wind farm interference, where the false echoes may be contoured and have a closed cell appearance, are less recognizable. We covered this last year. It's important to be familiar with wind farm locations. Wind farm echoes do not move. You can compare those with the surrounding echoes. One thing, though, that we can note is that wind farm interference is often not seen in the absence of AP producing inversions, if the wind farms, as in the Minneapolis case, are far enough away. If you have AP, you may also see the wind farm echoes. So where are the wind farm locations in the Minneapolis region? Here's a map that shows the different wind farm locations. You'll notice that there is an area to the south of the Minneapolis region that is fairly concentrated with Minneapolis Station, rather, that is fairly concentrated with wind farms. And also each one of the radars in the local radars within the Minneapolis region have their own sort of wind farm pattern where these echoes appear most frequently. So let's talk about other thunderstorm forecast products. It's important to note that even though there are some people that are constantly looking for that silver bullet, there isn't one to getting an accurate view of the future. All thunderstorm forecast products have their limitations and shortcomings. Models and algorithms are but indicators of future weather scenarios, but we're bringing a few of these up because currently some of these products are used by the Severe Weather Desk at the Command Center for choosing routes around thunderstorms and picking programs. These include the CCFP and CAUSE, the COSPA, and the HER model. But two others we want to discuss here are the SREF model and also LAMP. The SREF or SREF is short for Short Range Ensemble Forecast. It takes 22 different forecasting models to produce a probabilistic forecast out 6 hours at 3, 9, 15, and 21 UTC. It focuses on the prediction of high-impact weather, including thunderstorms and severe thunderstorms. What they look at are areas where the probabilities are 31% or greater, and that seems to correlate well with future thunderstorm areas. They believe it's been proven effective between mid-May and through mid-September. It forecasts actually 39 one-hour updates into the future. The LAMP forecast is available also on the web. It's a lightning probability, and the potential grids are issued every hour for 14 forecast projections. There are hourly increments for the first 7 hours and then 2-hour increments thereafter. You can see the probability of lightning in certain areas of the contiguous United States in those periods. And where do you find these products in addition to others? There is a website that is important, I think, that is actually very useful to use for traffic managers and persons interested in future thunderstorm locations. It's the Traffic Flow Management Portal. It lists a series of icons, look like apps almost, that you can choose and look at these individual products. And these are available at this website, the testbed.aviationweather.gov page. And feel free to take a look at that. There are a lot of useful products on there for forecasting and monitoring thunderstorm activity. So question 10. Which weather hazard category is responsible for the most accidents to Part 121 commercial aircraft? Is it ceilings and visibilities, icing, turbulence and convection, or terminal crosswinds? And since this is a thunderstorm module, you probably should say C. In a 1996-2006 study, the ratio of accidents from turbulence and convection to total weather-related accidents for commercial aircraft ranged from 65% to 94% for any given year. So by far, thunderstorms and turbulence are the most important hazards to the majority of the flying public, including passengers. The greatest opportunity for reducing injury and fatalities lies with programs that reduce the impact from turbulence and convection. So as a controller, you have an important role in helping aircraft avoid encounters with thunderstorms, but also the turbulence they cause. Please keep on top of developing thunderstorm situations and pay attention to locations of reported turbulence around thunderstorms to properly advise pilots on routes and altitudes. So how storm-wise are you? Well, if you had 8 to 10 right answers, congratulations. You have earned supercell status. On the other hand, if you had less than 8 right answers, you probably could use some improvement, maybe a little study on thunderstorm activity. At any rate, thanks for your attention, and have a great day.